Okay, in part one, we looked at the whole aspect of heteroscedasticity until to a point where we looked at the various tests of heteroscedasticity. Now we are going to look at as to how do we deal with it. Of course, we said in the first instance we can already deal with it by estimating the heteroscedasticity robust standard errors. But now, if you have certain type of other heteroscedasticity, then we can use other remedies. One such remedy is estimating the so-called weighted least square estimation. Now, what does this weighted least square estimation involves? First of all, we actually should know that heteroscedasticity, sometimes it can be known, sometimes it can be unknown, or its form might not be known, and its form, or it might be known. It differs. So, but now what we know is that the form of heteroscedasticity is only known up until a multiplicative constant. All right. So, and that's why we can use this weighted least square to deal with that. So what we simply do is that when we assign weights to each of these variables, then we actually then know that then it actually implies that, so you divide each, if this is our original function, our just like our generic multiple regression, where we have y is a function of beta naught, beta 1 x1 up until beta k xk, depending on how many variables we have there. So if we divide each of these by hi, we take hi to be the divider for to use it as a way to divide each variable. We'll actually see that what what will then happen is that by assigning weights to each of these variable, we actually transform that variable. Sorry, we transform that model, and then it becomes this, and we indicate it with asterisks. This is basically now a transformed model. And it also here shows that the functional form of the heteroscedasticity is known. Now, once you do that, for example, if we use savings and income, so we know that savings is a function of income. So when you assign weight, if this is our normal equation where we say saving is a function of income, so if we divide every variable by income, then we have savings here divided by income, then beta naught 1 over, there's whatever square root of income plus beta 1 income over income. Now we actually know that if we do that, we are going to, so here you see you are going to remain with savings over the square root of income is equal to beta naught plus 1 over that plus beta 1. Now you see that here just this becomes 1. And now what you should also take note here is that this model will no longer have an intercept. It becomes an interceptless model. So now what you see is that the transformed model, we have a constant variance because of this. Income by income just become 1, so it's a constant. So we have a constant variance. So now we are saying if all other assumptions holds well, then we can apply the OLS on this transformed model, and it can actually yield the best linear unbiased estimators. So, and that's why we say when we apply the OLS on the transformed model, that is actually what we refer to as the weighted least square. Now, remember that with the usual OLS, we minimize the error. We take the summation of the error, we minimize the error because we want a small variation between the actual and expected. So in the case of a weighted least square, we are basically minimizing the weighted sum residuals of squares and where we assign weight. And that's why we're saying in this instance, so the observations with the larger variances get assigned smaller weight, because that's actually what we do with optimization problem, whereas the observations with smaller variances will then get larger weight, because if we assign bigger weights to observations with larger variance, then it's going to cause a distortion. So if we want to minimize that effect, so we assign a smaller weight to it. And so that is the essence of this weighted least square. It's considered to be more efficient because of that, allocation of larger weights to the smaller observations with smaller variances, and assign smaller weight to observations with larger variances. And then we also know that now when we do that, the standard errors of the weighted least square estimators is usually smaller, and that is basically in line with the assumption of them being more efficient. And you should also know that the weighted least square is nothing else, but it's basically a special case of the generalized least square method. Now, sometimes sometimes you have certain variables that are already given in like averages. For example, you are given average values for city, country, state, firm, etc. So this one, for example, if we take this example, here you can see that everything is averaged. So when it's averaged, so what happens is that, so the error variance here, you see this is the error variance. So this error variance will only be homoscedastic at the employee level if we take this example, because here we are looking at the average contribution to pension plan in the firm. So we take the average earnings percentage contributed to the plan. So, and then here we have a heteroscedastic error term. The fact that we are already dealing with averages, so when you assign weights, so that what is going to happen here is that you will have a variance that is going to be homoscedastic if you look at it from an employee level. Okay, so, and that's why we say with weighted least square, you are basically remedying to move from heteroscedasticity to homoscedastic. Okay, so that's basically how we deal with that thing. Now, sometimes we have unknown heteroscedasticity function, and in this case, we can no longer really just use the weighted least square alone, but rather we can use the so-called feasible generalized least square. If we take this functional form, so if we take this form, if for example the error in the variance term or the heteroscedasticity takes an exponential functional form. For example, here usually they will do that because they want to ensure that we have positive value. So then what will happen is that, and you can also see that here in this case, the error term is multiplicative in the function. Okay, so if we transform this model into logs, then what we have to do is that if you come to this exponent, we will have to use the inverse values of the estimated heteroscedasticity function as a weighted least square. In other words, we have to use the inverse of that that function as weights. And once we do that, then that means that the feasible generalized least square is consistent and asymptotically, and it's also considered to be more efficient than the ordinary least square. Here is just an example. You can just take time and go through it. But as I said, we don't really have to worry much about with this example because we will do the explanations in e-views. But here again, I just want to bring you to attention. So here, for example, they use the British pattern to test for heteroscedasticity, and you can see here that because since the probability is 0.00 is actually less than 0.05, and so therefore we can reject the null hypothesis of homoscedastic or homoscedasticity, so meaning there is a problem of heteroscedasticity. But if this probability was greater than 0.05, we were going to not reject that homoscedasticity, and that's actually what we want in our model. And so you can actually see that when you can actually see that where if you estimate a feasible generalized least square, that makes things much more better than the usual OLS if there is a problem of heteroscedasticity. Now, what if now the question will be, what if what we have assumed is wrong? What if the heteroscedasticity function that we have assumed is wrong? If there is such a misspecification in terms of a function, the weighted least square will still remain consistent under the under the multiple linear regression assumptions 1 to 4. So remember that we have 10 assumptions, but the robust standard errors should be computed. In other words, you cannot just use the ordinary standard error. And I'm going to show you how to um, estimate for those robust standard error. But what you should know is that your weighted least square will still be consistent, irrespective. It's just that you need to compute the robust standard error. And then what we should also know is that obviously if we have a situation whereby the ordinary least square and weighted least square are producing different estimates, then this actually indicates that something is wrong with the other assumptions, like 1 to 4. Okay, and so the other thing is as well is that if there is a strong heteroscedasticity present in the model, then it's always better to use the wrong form so that you can increase the efficiency, because the right functional form will actually decrease the efficiency of the estimators. And that's why we rather go with the wrong, not the functional form of the model, but the functional form of heteroscedasticity that we are dealing with, whether it's multiplicative or is not multiplicative or whatever the case is. And then, okay, obviously, just like in the previous case, the previous chapter, when you were dealing with the linear probability model, like your probit model or your logit model, or where you have a dependent variable being a binary, taking a value of 0 or taking a value of 1, you can also have a problem of heteroscedasticity. So, and in such models, you can also apply the weighted least square method to remedy the problem. So, and that's why we say in the in the in the in the linear probability model, the exact form of heteroscedasticity is actually known. Because it's known, then you can actually know how to remedy it. And that's why we said you can use the inverse values as the weighted. Okay. But now the thing is, this might not be applicable if these coefficients or the predictions, these coefficients like beta 1 is below 0 or greater than 1. Why do you think is the case? It is the case because our model tells us that those predictions must be between 0 and 1. 0 is when the likelihood of an event did not occur, and 1 is when the likelihood of an event to occur. So, and anything beyond 1 or below 1, then these predictions become invalid and you can no longer use the weighted least square. So that is the only main thing that you should take note of. So if that is not the case, then it's rather best, if this is not the case, then rather use the OLS with a robust standard error. And that is basically it. Okay, so that brings us to the end of the lecture.